All right, in 2.1, we're talking about location and distribution. And the first one we measure that is percentiles. So here's the definition. The p percentile of a distribution is the value with p% of observations at or below it. Okay, this happens all the time with like SAT, ACT scores. Let's say you're at the 85th percentile. That means that's 85% of the people scored what you did or below what you did. Okay, so it's at or below. It's both of those things. Okay, it could be both of those things. So, for example, if Jenny's in a class of 25 students and she makes an 86 on her test, she's the 4th highest score. Is her percentile the same as the percent correct? Well, she made 86% correct. Let's see what her percentile is. Well, so the first thing I would do is count down to see what her fourth down would be. So I count down 25, 24, 23, 22. So I find that percent. She's 22nd out of 25, which puts her at the 88th percentile. So her percentile is not the same as her percent correct. Okay, she's at the 88th percentile. It's not the same as her score on the test. All right, so let's try another example. Wins in Major League Baseball. The stem plot shows the number of wins for each of 30 Major League Baseball teams in 2009. Calculate and interpret the percentiles for the Colorado Rockies, who had 92 wins. All right, so first of all, I need to find the location of 92. So I find it right here. There's the 9, there's the 2. And so I then need to find out, okay, well, if I count from lowest to highest, there's 30 of them, right? So where does this one rank? So if I count, I'm going to count backwards because it's closer to the high end. 30, 29, 28, 27, 26, 25. So this is 25 out of 30. And I find that percent. So that would be at the 83rd percentile. So let's say the Rockies, who had 92 wins, is at the 83rd percentile. All right, same process for New York Yankees, who won 103. So I find 103 right there. Well, that's the 30th spot out of 30. So 30 out of 30 is 1. So it's the 100th percentile. Yankees, who had 103 wins, is at the 100th percentile. Cleveland Indians had 65 wins. So notice there's 2 65s. We don't know which one that is. But remember the definition is at or below. So 65, I'm going to count both of them. So I count them and count down. 1, 2, 3, 4, 5. So at the 5th location, out of 30, that's 17.17. So I'd say the Indians, who had 65 wins, is at the 17th percentile. Now I want you to notice in my interpretations, I don't say is on the percentile. I always say it's at the percentile. It's not in a percentile, it's at a percentile. It does matter, y'all. It does matter. Okay, another example for you. It's state median household income. That's what this graph is telling us. So this is what's called a cumulative relative frequency graph, or an ogive. And it shows the distribution of median household incomes for the 50 states and the District of Columbia. So what this is doing is it's counting up to 100%, if you see the y-axis. So it just kind of keeps building up. So how do you read these? Well, you have to pay attention to the axis and read from what you know. So first question is, California, with a median household income of $57,445, is at what percentile? Okay, the percentiles are on the y-axis. The incomes are on the x. So they gave it as an income, so I'm going to start finding that income. 57,000, about right here, is at what percentile? So I start here and then I read to the y-axis. That's around 80%. So I would say the median household income of $57,445 is at approximately the 80th percentile. It's not exact, but it's approximately the 80th percentile. B, what is the 25th percentile for this distribution? Okay, so now notice it starts us at percentile. Okay, well, that means I need to start from the y-axis at 25%, roughly there, and read down. That's about $45,000. Okay, the 25th percentile is approximately $45,000. Another name for this is Q1. It's quartile 1, right? Q1 is 25%. Okay, so from an ogive, you can actually figure out the shape of the distribution if you had done a dot plot or a histogram or something like that. So let me help you see this, okay? Where's the original graph the steepest? All right, so you're looking for where's the highest slope, okay? In this case, it's increasing the fastest right in here, right? So what does this indicate about the distribution? Okay, if you want to think of it kind of like a box plot, this is the box part. Okay, where does that fall? This falls between 40 and 55K, right? And that's like 25 to 75% of our data. That's a big chunk of data. It falls right here. It's not exactly in the center of the x-axis, but it is right here. So since the steepest part of our ogive is between 40,000 and 55,000, representing between 5 and 75% of the data, the remaining 25% is in the tail, okay? That tail is on the high end of the income, so it's positively skewed, that extra tail. So that would mean that it's slightly right skewed. It's not terribly skewed, but it's slightly right skewed because the tail is over here on the right. Now, what does that mean? What would it look like otherwise? Well, so this is what we have. It's steepest in the lower values. That's what's happening here. So that gives us a right skewed distribution. If that steepness was dead on in the center, that would be an indicator of a symmetric distribution. If the steepness was on the high end, but the tail falls on the low end, that would be a left skewed, like this. Okay, so you can tell some shape from these ogives. Kind of handy. Okay, so in the second part of 2.1, we're going to talk about another way to measure location in a distribution. It's called a z-score. So let's start with an example. Macy's a 3-year-old female that is 100 centimeters tall. Brody, her 12-year-old brother, is 158 centimeters tall. Obviously, Brody is taller than Macy. But who's taller, relatively speaking? That is, relative to other kids of the same age. Who is taller? So according to the Centers of Disease Control and Prevention, the heights of 3-year-old females have a mean of 94.5 centimeters and a standard deviation of 4 centimeters. The mean height for 12-year-old males is 149 centimeters with a standard deviation of 8 centimeters. All right, so let's figure this out. Macy is 100 centimeters, and if I subtract the average from her, 94.5, she's 5.5 centimeters above the average girl her age. Brody is 158 centimeters, and I subtract the average of 149, he's 9 centimeters above the average boy. But that's not a great indicator because it's not factoring in what's the typical distance going to look like. So it's hard to compare these two, okay? We need to standardize them so that we can compare apples to apples, if you will. So you have to consider the typical deviation from the mean. You have to pull in this standard deviation and figure out how does that play into this? Because girls apparently vary less than boys do. Look at that. Girls vary by 4 centimeters, boys vary by 8. So we need to factor that in. So we use a z-score. So if I take her average, the difference in the average, she's above average, right? 5.5, and divide it by the standard deviations for girls her age, she's 1.375 deviations from the average height. Brody, if the standard deviation is 8, he's only 1.125 standard deviations from the average height of boys his age. So now we can really compare, and it appears that Macy's actually taller for her age than Brody is for his age. Okay? This is called creating the z-score. We're factoring in the distance from the mean and the average distance from the mean. So the z-score tells us how many standard deviations from the mean an observation falls and the direction it falls, okay? So here's the formula. You take the observation, subtract the mean of the sample, and you divide the standard deviation of the sample. This creates the z-score. So the unit for z-score is standard deviations. Now, if it's positive, that means the observation was greater than the mean. So it's how many standard deviations above the mean. If my z-score comes out negative, that just means it's below the mean. This observation value is lower than the average value. So, home run kings. Let's look at this example. Single season home run record for the Major League Baseball has been set just 3 times since Babe Ruth hit 60 home runs in 1927. Roger Maris hit 61 in 61. Mark McGwire hit 70 in 98. Barry Bonds hit 73 in 2001. And in an absolute sense, Barry Bonds had the best performance of these players because he hit the most home runs in a single season. However, in a relative sense, this may not be true. Baseball historians suggest that hitting a home run has been easier in some eras than others. This is due to many factors, including batters, quality of pitchers, hardness of the baseball, dimensions of the ballparks, and possible use of performance-enhancing drugs. To make a fair comparison, we should see how these performances rate relative to others hitting during the same season. All right, big setup. Here's the data table. So it says to calculate the standardized score for each player and then compare it. All right, so let's take our table of values and let's label it. The home run column is our observations per player, or the mean of the season. And S is the standard deviation for the season. Okay, so we're comparing their seasons to each other. So let's do this first with Babe Ruth. Okay, he had 60 home runs. The average was 7.2 that year. And you divide it by the standard deviation. Babe Ruth gets a z-score of 5.44. So that means he's 5.44 standard deviations above the mean. So we continue on with Roger Maris. He had 61. We subtract the mean number of home runs that year, divided by the standard deviation, and he has a z-score of 3.15. Mark McGwire had 70 minus 20.7 divided by 12.7. He has a z-score of 3.88. And then Barry Bonds with 73, average that year was 21.4, and divided by 13.2, he has a z-score of 3.91. Now, remember Babe Ruth was 5.44. So then it says to compare. Well, let's think about this. All the players are above the mean for their respective years. Notice they're all positive z-scores. However, Babe Ruth is the home run champ, relatively speaking. He far outweighed the other players. In 2001, Arizona Diamondback Mark Grace's home run total had a standardized score or a z-score of negative 0.48. Interpret the value and calculate the number of home runs he hit. So interpreting first, okay? So Grace hit 0.48 standard deviations below the mean of 21.4 home runs in 2001. Okay? We know the 2001 from the previous slide, or how many home runs were in the previous slide. Now, notice it says below the mean, and I don't have a negative 0.48 here and say below. That negative is accounted for by the word below, so don't double do it, okay? Now, to calculate the number of home runs he actually hit, we're going to use our Zscore formula. The observation is what we don't know, okay? So I'm going to plug in what I do know. I do know that his z-score is negative 0.48. I do know that the average in 2001 was 21.4 and the standard deviation was 13.2. So now it's just algebra to solve. I'm going to multiply both sides by 13.2. And then I'm going to add 21.4 to both sides. And I get approximately 15. You can't have half a home run, so we're just going to round it to 15. So interpret this, I would say Grace hit about 15 home runs that year. That's all there is to it.